My name is Paulo. I work at Edited. We are a technology company, and we provide analytics for retail business. So what we do is, oh yeah, so that's the agenda for people who like that. So what we do is we scrape the web, specifically fashion retailers' websites, and we get like all the products, pricing information, pictures, names, description, everything. We organize it, classified it, run analytics on it. So we have on our database now more than 100 million products. Each product contains multiple prices over time. So this sums up to more than 800 billion data points, more than 90,000 brands. And so we organize this data and we kind of sell it back to the retailers in an organized, summarized way that they can easily use in their pricing decisions. These are some of our clients. So we have like Topshop, Misguided, all these like fashion retailers, and we help them to have the right product at the right price at the right time. And in order to do that, we have loads of classifiers going on, both text and image. And here I will concentrate in convolutional neural networks. I'm seeing that it's just a few of you, so I imagine that you are the guys that kind of already know convolutional neural networks, deep learning, and all this kind of stuff. So usually how this image recognition works is that you get a neural network architecture that usually was trained on ImageNet, which is a challenge of classifying into 1,000 tasks. And you get this neural network and you train to recognize something, a simple task, like someone did something for if it was a hot dog or not. So you get this architecture that have the potential to classify 1,000 categories, and you do hot dog or not. And when you have another task, if it's a cat or a dog, you train another one to do that. So what I try to do, what I've been studying in the last months, is how can we share this architecture to do multiple tasks, right? So as I explained, in a single task classifier, what you have is a set of n mutual exclusive labels that you're trying to classify in. And if you want more than one set of labels, you need another classifier. While in multitask, what we expect, and I will show you some results in the end, is to classify in multiple sets of labels in one go. This hopefully will save a lot of processing time, will improve the embedding or the vector representation of that. But most, all those like Keras and Cafe, they are not exactly made for that, so you need to do a bit of customization in it. Also, the data sets are usually not in the format. Usually you have your data sets of hot dogs and not hot dogs, and your data set of cats and dogs, but you don't have the data set of this is not a hot dog and this is a cat. You don't have this multiple label in most of our data sets. So this can be a little bit challenging to get the data in that format or work with the data in that format in a multitask way. And training is a little bit harder to converge. We'll also take a look at that because when you're doing it with one task and with this neural networks architecture, it kind of converts easily now. Nowadays, it's kind of easy to just plug your data there, retrain it. Usually it's all right, but with more than one task, sometimes it's a little bit shaky. So if you guys ever seen convolutional neural networks, you saw this thousands of times. So I will just simplify this a little bit. So you have your input image, you have a bunch of convolutions, and you have a classifier. That's basically it. So I like to think of these components as being like mix and match. You can change your input, you can change your convolutions, and you can change your classifier. So that's how we'll be working in a very simplified way. That's how an image recognition classifier works. You have an image input, you have a set of convolutions that will process this input, and you will transform into vectors, and these vectors will be classified in the end. So what I'm proposing is sharing this convolutional layer instead of training a new one between the tasks. And if the tasks are too different, you can even put another convolution there just for getting a little bit better in this task. But in the example today, we'll just do that. So I'm using Keras to do, I think that Keras is brilliant in the sense that it makes convolutional neural network way easier to do. So there are three main steps. So we are having a problem with the display port, so the colors are a bit off. Our designer editor will be really sad when she sees the video and that the colors don't match to what she imagined. But I think that we will all survive. So they're setting the model architecture, generating your training batches, and then calculating the loss function. Loss function is kind of the error. It's kind of how you penalize the neural network when you get a classification wrong. So so imagine that you receive an image input. You get a convolution already, a famous architecture like your VGGs or your ResNets or whatever. And what we are going to do is we are not going to import the classifier. We're going to build our own classifier. And we are going to combine the output of them in one single vector. So the way that we do that with Keras, it's quite simple. You import. So I'm using exception. It's kind of a new architecture from the guy that invented Keras. And I'm specifying here, do not include the top. So do not include the classifier in the end. Average whatever it's getting to the last convolutional layer to a vector. And I'm specifying that as an input, I'm using pictures of 299 by 299 pixels. It's kind of the standard nowadays. And then I'm getting the output of this part, and I'm adding a dense layer, a dense classification layer with the number of classes of my first task. I'm using the model output as input here. And then I'm adding a new one with the number of classes of the second classifier. So for instance, if you're classifying, vehicles, and you want to classify if it's a train, a boat, or a car, this will be 3 classes. And if your second task is these vehicles, I want to know the color, if they are green or red or whatever, this will be your 2 classes here. Then what I'm doing is I'm concatenating, Keras have this concatenate function. I'm concatenating the output of these classifiers into one unique vector, and I'm putting all of this in a model. So it is quite easy. Oh, I can move this. Oh, even easier. I don't need to go there. Oh. The modern world, technology. Yeah. So I'll send you guys a presentation after if you want to test the code or whatever. But the point here is that quite easy to build this sort of architecture with Keras. So also Keras come with, by the way, I'm not being paid for Keras. If there's anyone from Keras that want to give me a t-shirt or anything, I would be really happy with that. So Keras have a really good image data generator because in this sort of tasks, you need to augment your data a lot because data is never enough. So what this image data generation function in Keras do, it kind of crops the image randomly, rotates it a little bit. So it's really easy to do. You just say, okay, go to this folder where I have all my pictures and run all these transformations there. But this is optimized for one task. So what you need to do is you need to create multiples of this, and you need to pay attention when you're generating the batches that you have enough examples of each one of the generator into your batch. And obviously, that it fits on your GPU. Which can get expensive. And now is the hard part, is how do you calculate the loss function? And unfortunately, it's the worst color slide that we have. So Keras also allow you to build custom loss functions. The problem with that is that they want you to write in the backend symbolic format that I had no idea what it was, but it was kind of TensorFlow language. So I would just give an example that unfortunately will be hard to read. But so imagine that you have your data set of vehicles. So for your data set of vehicles, you know all the labels, all the pictures that you have that. You know that they are boats, or that they are cars, or that they are trains, or I forgot the example that I gave. But I don't have the labels from my second task for this data set. And the classifier will predict it anyway. I forgot that I can point it here. But the classifier will predict it anyway. So you have the label, and you have a prediction for this task, and you have a prediction for this other task, but you will not have the label for this. So the way that I customize a loss function is that I'm masking. If I identify that the file come from the first task database, I'm masking everything generated from the second task, and I'm calculating the error only on this. Or else, I would not be able to calculate the error because I would not know the label. I do the same thing for the second, if the file comes from the second task. I just mask everything predicted for the first task, and I calculate the loss. And then I do the sum of the losses, and the sum of these losses is what I'm trying to minimize. And if you have a task that is more important than the other for you, you can give weights for each one of this and try to be better in one of them. And this is a bit of the symbolic language. So it is easy, it's just annoying that instead of just writing sum, you need to import k, which is like the Keras backend, and say, okay, it's k sum instead of just sum. Or I cannot just put like 0 or a 0 like. I need to import this epsilon constant, say that it is a constant. So it's easy to do, especially like if you know Python, you'll be probably comfortable with this. But for me, it was like I tried a lot of times and I couldn't make it work. Then I saw like obviously as everyone on Stack Overflow, someone that say, oh, you need to use the backend language. Oh, thank you. And then you just remember to specify that your loss will be your new created custom loss. You can even also create custom accuracy, but this is another kind of worms. And now I'll go some more results of actually training this with edited data. So as I said, we work with fashion retailers. So our data is basically fashion products. So what I'll try to do is I'll get an image. I'll run through a shared convolutional layer from the exception architecture. And I'll try to classify into colors, if it's a multicolored or if it's a single color, and if the picture have a human model or it's just the product. So the data set kind of looks like this. This is multicolored, this is fashion. And that is not multicolored, also very fashion. This is with a model. As I said, like the color in the display doesn't let you identify, but I think that we can say that it is a human. That one is not a human. So this is with a model and without a model. And these are examples of colors. So the first one is actually gray, trust me. The second one is green. The third one is white, but notice that there's like a complex background. So we want to be able to also classify even with like the most, because people in fashion can be quite creative. So you would want just a picture of a product over a white background. This doesn't happen all the time. People like on the beach with the sun and like on the tube or whatever. Or red. Actually, again, as is fashion, we have actually 21 colors, which make this task really hard because a lot of colors for me are the same, like green and lime. I look at it and say, but anyway, fashion. So when I train it, this is what I mean by it's harder to converge. So usually when you train these kind of things in one task, you see like a very smooth decay of your training loss. But when you do that with multiple tasks, it goes all over the place. But on average, it's decreasing. It's kind of what matters. It's just that at some point you just leave it running by like 4 or 5 epochs and say, this is not working. No, if it run a little bit more, eventually it will converge. And this, I didn't have time yet to take a look at the results at each one of the epochs. But what I guess is happening is that, so it got really good in one of the tasks and bad in the other, and he tried to kind of average it, and it got a little worse than both. And it goes learning the weights to try to...
There's validation loss, it's not training.
I'm sorry?
It's validation loss.
Oh yeah, it's like, I'm calling kind of, so this is the test set, to be honest. So yeah, this is the test data that I'm calling validation. This is during training, testing on the test data. I'm sorry?
You're not using the gradients from the validation.
I'm using the gradients for each one of the epoch.
From the training, yeah.
From the training examples, I'm applying on the test examples that were unseen by the network. So I can test if it's robust to, if it's not overfitting. Excellent point. Yes, And here's some of the results that I got. So if I do each one of these tasks individually as a single task classifier, each one of them take around 37 milliseconds. God blessing me again. But the truth is, if you want to do all of this, you need to count them sequentially if you're doing single task. So this ended up being almost 120 milliseconds. But if you do that with a multitask classifier, and this will be a really good time for the bells, you can classify the three tasks in just like 40 milliseconds. So you're gaining a lot of time by doing that. And you know, as I said, we have like 100 million products in our database. So like 48 milliseconds times 100 million products, it's around a lot of days. So you're saving like probably a month of processing time. And you might imagine that this comes to the cost of losing accuracy, but actually the accuracy is pretty much the same. So on the blue color is doing it as a single task. On the purple one is a multitask. So you see that only on the multicolor knot, I lost like 1 percentage point of accuracy. For the other ones, pretty much the same. And see how the colors is a lower accuracy task because of the confusion between the limes and the greens, and the blue and the teals, and the aquas, and all the fashion. Yeah, and also I want to test how this impacts the embedding or the vector representation of each one of these products. So what I did, I trained the neural network, I cut off the classification part, and I take the output out of the convolution. And this is a vector of around 2048 dimensions. But now we have techniques to reduce the dimensionality. The famous one is TSNE, and it reduces to a two-dimensional vector space, and we can plot. So this is the raw data. And what we can do, and this will be disappointing for me because we will overlay the colors labels, but it will not look very good because of like the projector. So I swear, I'm blaming the, sorry projector, I don't want to blame you anymore. So this is overlaying the color labels over the raw data, and that one is overlaying the with model or without a model. Unfortunately, you guys cannot see. I'll send you the presentation so you can take a look. The with model or without model doesn't have as much data because I don't have label for all the examples of the with or without model as I have for colors. But the cool thing is that you can identify some groups. So here, you guys gotta trust me on that, but this is the red color group, the red labeled products, and this is also the red labeled products. And here, yeah, I have this. This is where the same products are for with or without model, and you gotta trust me on this one too, but they have different labels when I'm looking here at the data. And the cool thing is that if I take a look closer to these products, what I see is that the vector representation was actually able to group together things that are red and very similar tones of red and without a model, and things that are red, very similar shades of red, and with a model on it. If we take a look at the same thing with my favorite colors, lime, this is not green, this is lime. They also have a similar pattern of having like two groups separated, and same thing with and without model, having like two groups separated. And when we take a look at it, we can see that the embedding was strong enough to group together things that have similar shades of green and don't have a model, and in the other group, things that have a similar shade of green and have a model. So, so it's been strong enough to do all these sorts of tasks and in an efficient way without losing accuracy. I tried to push it a little bit further, and I did a classifier with doing 9 tasks. This was the maximum that I can do in my GPU. My GPU got 8 giga of memory, I think. And the best that I can do was, for this architecture, was 18 examples. So I did 9 tasks, and for each one of the tasks, when I was generating the batches, I got 2 examples of each one of the tasks to build it. So this was able to identify that these have something called sequence that someone told me is the shiny things that they put in, again, fashion. This have no straps. This got like a V-neck kind of thing. This got a model. So it was able to, it's not multicolored. So it was able to identify all these things at once. Same thing for this other example. This one doesn't have the sequin things, but have frills or something called ruffles. Is sleeveless, have a crew neck, doesn't have a model, doesn't have like studs or fringing, this kind of stuff. Fringing, I also learned that is this thing. So this one have fringing, don't have like ruffles. This one have a strap. It's also a V-neck, have a model. This one I got sequins and fringing, so this is a lot of fashion in one product. Long sleeves, crew neck. I do recommend if you're going to a party. And so yeah, that's pretty much what I had to show to you guys. So some of the challenges that I've been facing is how to deal with like the batch sizes and the number of tests that you can run at once. The convergence, I'm trying to smooth it out to make it less shaky during the epochs. And there's very little literature on doing multitask convolutional neural networks. So how do I design the network is still a challenge. It's still something that I've been studying. It's an interesting field. I'll be here all day. If you guys like this kind of things and want to discuss, I'll be happy with that. Or you can email me on paulo@edited.com or send like a Twitter thing. It will be good. Our marketing team will love it. That's it. Thank you, guys. Thank you. Do we have time? Do we have time for questions?
We've got 3 minutes for questions.
All right. If anyone have any question. Yes, you?
Does it get confusing when you're talking about training models on models?
Yes, training models on models, yes. So yeah, it is a bit confusing, but hopefully you all understand. Model. Model. There's a difference. Any other question? Yes, you?
Probably dumb question, but is there any, do you run these on GPU clusters that you yourselves have built, or just go to the cloud?
Excellent question. So, because when I started doing this, I had no idea what a GPU was. So this was like 2 or 3 years ago. So we started having our own physical machine that is still there in the office with a GPU that I think had 4 gigabytes. But soon enough, this became too little for us. So now we have, I think, 4 servers that with 4 GPU with a GPU of 8 gigas servers that I think are hosted on Germany, right?
Yeah.
Yeah, and we train on these servers. They are not connected in a sense that we haven't used yet multi-GPU capabilities. Each one of our data scientists have this server, and we train there.
But these are GPUs and servers that you have bought and you are running, as opposed to you pay by the hour for Amazon.
Yeah, it's not AWS. It's just hosted bare metal.
Yes.
Yeah, by someone else. We just rented by month.
Okay, somebody else built it, but it's not full-blown cloud.
Yeah, it's not
Another
cloud.
company, right? Thank you.
Yeah, I'm not a dev. I don't understand these questions. I'm sorry. So I have my team to help me. Yes, as I said. And also, we are hiring. If you guys like this kind of stuff and want to talk with us. We have a beautiful stand there with a polar bear and socks. Any other questions? Yes?
Sorry, this is not a technical
Why the
question
microphone get there?
It's more like curiosity about your background. What did you do before edited? And
Okay. So I studied engineer a long time ago, like civil engineer, heavy construction. Then I specialized in transport engineer, and I worked for airlines. While working for airlines, I did a lot of math for them, like O&D optimization, this kind of stuff. Then I got bored and went to do a master's in applied mathematics. And it was when data science was becoming a thing. So I got this like in the beginning, and since then I've been doing like models and stuff. Models. You get the idea, I guess. There was a question there, I guess.
We pass the mic back.
You mentioned. Yeah, okay. So you mentioned basically that there is a bit of an issue with having like a proper data set that is labeled correctly.
Yes.
Does that mean that you have to construct these data sets yourselves?
Unfortunately, a lot of times, yes, when I'm doing experimentation. So when I'm doing experimentation by myself and I don't want to use like company resources in something that might lead me nowhere, what I do is I build myself. So as I said, I had no idea what like fringes or frills were. So what I do is I search for it on our app. We have like a fashion app, and I download the pictures and I kind of build the training set myself. When this is working and I say, okay, I think that this is a really good idea, we have a QA team that help us building the training sets.
Okay.
That's kind of how it is.
You can always pay for beers as well.
Yeah.
Actually, ground rules for you. I do that.
Yeah, so
Just one more.
it's related to what she asked. How many labeled images would you need in a training set to get okay-ish performance?
Nobody really knows. Anyone that tell you this is specific number
Yeah.
is bullshit. I try to always have like 1,000 of each label.
Class.
So 1,000 for each label is kind of what I'm starting to go for, to have like a good working model that I can show people.
And then you would go to 10,000, whatever.
Exactly. When we are ready to put this on production, we retrain again.
Yeah,
and
yeah, yeah.
during this part, they'll say, okay, now we need like 5,000
Yeah,
or
yeah.
10,000.
Okay, cool. Thank you.
The short answer is you need a lot of data.
Yeah.
All right.
Thank you.
All right. Thank you very much. All right.